You remember that the temperature of a planet is defined by the equation energy in equals energy out. That's a simple equation, but when we start to apply it to the Earth's climate system, it gets a little more complicated. Here we see on the left that there's 342 watts per square meter coming into the Earth from the sun. Now, what does that mean? 342 watts is what? 300 watt light bulbs and a 40 watt light bulb. And each square meter of Earth, each 1 yard by 1 yard piece of Earth, absorbs on average, again, averaged over the seasons, averaged over the year, averaged over the latitudes, 342 watts per square meter. What happens to that? Well, you recall from the first part of this class that in fact 31% of it just reflects back into space and doesn't contribute at all to the warming of the planet. And here you see in this diagram 77 watts per square meter reflecting off the clouds and the aerosol particles in the atmosphere, and another 30 watts per square meter reflecting off the ice caps and the snow fields and the deserts of the Earth. So 107 out of that 342 watts, or 31%, as I said earlier, reflects back into space and doesn't contribute. But the rest of it gets absorbed, both by the atmosphere and by the ground. But, as the other side of the equation suggests, that has to get radiated into space, so the energy out takes several forms. Some of it goes into warming the atmosphere, some of it goes into evaporating water that ultimately makes clouds, and some of it tries to escape from the surface of the Earth, but is trapped by the greenhouse gases, that blanket of special absorbing molecules, carbon dioxide, methane, nitrous oxides, etc., that reflect it back to the Earth. But any of these components of the Earth's climate system are, of course, subject to change. So, for example, when we have an ice age, much more of the land, most of the northern hemisphere, is covered with a big sheet of white, shiny ice. And that means more energy is reflected back into space. The reflected component from the ground increases. Alternatively, when we have an unusually warm period, that means that the atmosphere gets warmer and more water vapor is evaporated and more clouds are produced. Or if we have the CO2 content of the atmosphere, one of the greenhouse gases, rise, as we have seen it is steadily doing, then the amount of radiation trapped that tries to leave gets reflected back to the surface of the Earth and keeps the Earth warmer. So we have this complex set of relationships to define the energy in equals energy out equation, and to figure it all out, we need lots more data. We saw earlier that the Earth's orbit and the tilt of its axis vary over timescales of tens of thousands to hundreds of thousands of years. How do those changes affect Earth's climate? And can our models of energy in equals energy out account for that?